Hello everybody. Today we're going to be looking at a classic probability puzzle, and we're going to be solving it using um, recursion and induction. So the problem states that n people are boarding a plane, but the first person has lost their seating ticket, so they have to take a random seat. Each person afterwards takes either their own seat if it's not taken, or if their seat is already taken, they have to um, pick a random seat. So this process continues on for all the people, and then when the last person goes to take their seat, what is the probability that someone is already sitting there? So I had seen this problem, I think, a few times, and the other day I was trying to solve it, and I ended up looking up the solution. Um, But then I sort of thought about it some more, and I came up with my own solution to this problem. So many times the problem is presented without the, the letter n. Usually it'll include some actual number, like 400 or 100, sort of to make it seem like the there is either a nice answer or you have to go through some really ugly calculations. So I'm just going to go right ahead and say that we're going to generalize this to n people, because actually this probability is always equal to 1/2, and that's what we'll be trying to show in this video. So let's take the case where you have two people. Just two people boarding a plane. I know it's kind of weird, but so um, so the first person will say, oh, and also this plane holds only n people. So there's not more than n seats, there's not less than n seats, there's exactly n seats. So let's say if n equals 2, then the first person obviously will either take his own seat, or he will take the other person's seat, or the last person's seat. So in this case, we can see that, of course, this is a 1/2 chance. Now let's try going up a step. If we have n equals 3, um, then the probability that someone takes this person's seat, well, there's a 1/3 chance that the first person takes it, right? Because, he has roaming chance to take one of these seats. So there's a one third chance that he takes it. Now, notice that if the first person takes his own seat, then everything is sort of settled, basically. Because each next person will just take their own seat because it for sure has not been taken yet. So, so for n equals 3, this person either takes the last person's seat, so that's just a 1/3 chance, or he could take, with 1/3 probability, he could take the second person's seat. And so now the second person has to go in here and say, okay, well, my seat's taken, so now I have to choose between these two seats. And so we see here that um, this is another 1/2 chance, because there's a 1/2 chance that the second person, upon seeing that his seat is taken, has to choose either the first person's seat or the last person's seat. So with 1/2 probability, he chooses the last person's seat, and so the last person's like, well, someone's in my seat. And we can evaluate this. This is 1/3 times 3/2, which comes out to 1/2. So we sort of get some notion that it's going to stay equal to 1/2 all the time. Now, um, so let's think about a more general case. Let's just say we have n seats. So again, the first person will have a 1 over n chance of taking the last person's seat. He also has a 1 over n chance of taking the second person's seat. What happens if he takes the second person's seat? Then the second person has to choose a random seat. But this is analogous to the case where you have n minus 1 people. So if we let p sub n denote the probability that if someone takes the last person's seat for n people, so p sub n equals the probability for n people, then we know that if the first person takes the second person's seat, then the second person will have to um, we basically have the case where there's n minus 1 people getting on a plane. So this is equal to 1 over n times p n minus 1. Likewise, if instead the first person chooses the third person's seat, then the second person will have to take their seat because it's not taken already. And then the third person will have to choose randomly, which corresponds to n minus 2 people. So here we're creating a recursion for p sub n. Okay, and so um, let's say that instead the first person takes the second to last person's seat. Okay, then everyone, the second person, the third person, the fourth person, dot dot dot, will take their own seat until we get to the second to last person, who will say, oh, well, my seat's taken, so I have to choose between the first person's seat and the last person's seat, which is analogous to P2, obviously. So we have generated this recursion. Now, what's more is that by, oh man, by establishing this recursion and by seeing that these first few probabilities are 1/2, we can use this recursion to try and prove our claim by induction. So to write this out more formally, we can say that suppose that P2 equals P3 equals dot 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 equals P sub n minus 1 equals 1/2. So this is actually called strong induction, where we assume that something holds from the base case on up. And so we see that with our recursive definition, we have 1 over n plus, and then here we can factor out a 1 over n. I'm using this equation now, 1 over n, and we can factor out, so we just have a bunch of 1/2s. How many 1/2s? We have n minus 2. If you don't see how I get that number, I basically subtract 1 from this list, basically, to count it. Sort of a bijection-y thing, because you have the consecutive integers from 2 to n minus 1, and if you subtract 1 from everything, you get the consecutive integers from 1 to n minus 2, and if you have the consecutive integers from 1 to k, that's k integers, so this is n minus 2 integers. So just a little side note. So we have inside this the sum p2 plus p3 on and on pn minus 1, that's n minus 2 times 1 half. Great. Well, now we have this mess in terms of n. Doesn't really look like it's going to equal 1 half, does it? Well, let's see. We can write this better as n minus 2 over 2n. And we can write 1 over n as 2 over 2n. Then we can just add, once we've established the common denominator, we just add the numerators, which 2 and n minus 2 gives n divided by 2n. Well, that just simplifies to 1 half. So let's recap. We looked at this problem and we looked at it in small cases, and we found out that there's actually a nice recursion. And by looking at the numerical values of some of the first few cases, we generated an assumption. That assumption is that the probability is always 1 half. Then we use that assumption and the recursive definition to show that we can use our assumption to prove that the next case must be 1 half. And since we already know that the first few cases are 1 half, that means that all cases are 1 half. This is the mathematical principle of induction, where you use an assumption and some base case, and you show that the assumption leads to the assumption for the next value. And so that's exactly what we did here. Thank you for watching. I'll see you in the next video.